Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper trending on X, published on February 16, 2026, just about a week ago. It introduces SynthSAEBench, a toolkit designed to generate large-scale synthetic data with realistic characteristics like feature correlation and hierarchy, effectively bridging the gap between noisy large language model benchmarks and small-scale experiments. The paper is titled SynthSAEBench, Evaluating Sparse Autoencoders on Scalable Realistic Synthetic Data, and as we'll see later, the results identify some major failure modes in current architectures, with significant implications for how we interpret model internals. To see how the benchmark constructs these realistic environments, Figure 1 breaks down the three core feature characteristics. The top section, labeled Hierarchy, organizes concepts into trees where child features like poodle depend on the activation of parents like dog. On the bottom left, the correlation panel models how features often activate together rather than in isolation. Meanwhile, the superposition diagram on the right shows how the system packs more features than available dimensions, creating the exact kind of noise and interference that sparse autoencoders must learn to disentangle. While Figure 2 translates those concepts into the actual generation pipeline for a single training activation. The process begins on the left by sampling correlated firings, where a multivariate Gaussian determines which features turn on, producing a binary vector Z. Next, the pipeline samples magnitudes for these active features to create an initial coefficient vector. Crucially, the enforce hierarchy step then filters this vector, zeroing out any child features whose parent nodes are inactive. Finally, the system applies the feature dictionary to output the dense activation vector A. So, having established the pipeline, Figure 5 reveals a striking disconnect between reconstruction and feature quality. The left panel tracks variance explained, where the green line for matching pursuit SAEs clearly dominates, implying excellent signal reconstruction. But in the middle and right panels, which measure ground truth feature recovery via MCC and probing F1, that same model performs poorly. Instead, the olive line for Matryoshka SAS rises to the top. This proves that optimizing purely for reconstruction can lead to overfitting noise rather than learning the true, meaningful features. Alright, Figure 7 digs deeper into this anomaly by testing how the models handle increasing levels of superposition noise. On the far left, plotting variance explained, notice the green line for matching pursuit SAEs. As the noise level on the x-axis goes up, every other architecture gets worse, which makes sense. But the matching pursuit model actually improves its reconstruction score. The middle and right panels expose the trap, though. Despite that high reconstruction, its feature quality scores flatline or drop, proving it is just overfitting the noise rather than learning the real features. So while the previous figures showed SAEs struggling to find the right features, Table 1 establishes the theoretical ceiling by training supervised logistic regression probes on the data. The results here are remarkably high. The bottom row highlights a mean F1 score of about 0.97, while the top row shows an AUC of nearly 1. Since the best SAE only achieved an F1 of 0.88, this gap proves that the features are mathematically recoverable, but current unsupervised methods are simply failing to extract them effectively. Wrapping up, two takeaways stand out. First, high reconstruction scores can be deceptive, often hiding models that overfit noise rather than learning true concepts. Second, since simple probes succeed where autoencoders fail, the bottleneck is clearly architectural. This toolkit finally allows researchers to debug those flaws before expensive scaling. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.